All right, so just like I mentioned before, what we're trying to do is figure out how do I take a polynomial like this, x squared plus 6x, and add some number like 20 or -3 or 5 or who knows what to turn this into a perfect square trinomial. And maybe you even know already what number needs to go here to make this a perfect square trinomial. But I'd like to kind of reinforce this with the algebra tiles. So if we have an x squared and we have 1, 2, 3, we'll do a little copy paste, 4, 5, 6, over there, 4, 5, 6 x's. And we need to know that, okay, well, we are allowed to add as many ones as we want, but we need to build a perfect square. So actually what we need to build here is a square. A square in the first place. So let's see what we have to do. So what I'm going to do is I'm going to kind of start arranging these into such a way that I want to get the outline or the dimensions of a square. So for instance, and note with these ones we can rotate as needed. So for instance, what if I put, you know, an x here? What if I put another one there? Come on, here we go. Another one. We'll put, how about 4 x's on this side, and we'll put 2 rotated this way. And I'm just gonna do a little copy paste here. Boop, and so we got our 6 x's, and we don't need you anymore. All right, so we have x squared, we've got 6 x's. Here's my question. Does this seem like it's gonna make the outline of a square? No, of course not. This is not gonna be a square. It's not. So I think we need to try again. Okay, what if I take one of these guys and instead of being that way, I kind of, aha. Okay, let's make this, oh, you know what? When I look at this now, it actually looks like I have the outlines of a square. That is amazing. Okay, and so the question is, how much more do we need? How many ones do we need to actually make this into a perfect square? Well, let's find out. We need 1, 2, 3. Maybe you can tell we're going to need a total of 9 of these. All right. And I'm just going to kind of put these in a slightly different color. Maybe I can do this in, I don't know, green. Let's do line color green. Ah, check it out. So these were the 9 that we had to add to make this into a square. What do I think this means? I think that if you have x squared plus 1, 2, 3, 4, 5, 6x, and you want to make it into a perfect square, you need to add 9. Now here's my question. What perfect square does this create? Maybe you already know. Well, I think we have x, right? So this is the dimension of x. 1, 2, 3. I think we have x plus 3 times x plus 3. We have the quantity of x plus 3 quantity squared. Amazing. So what we've done is we have completed the square. We quite literally completed a square here, and we've also completed a square kind of here, algebraically, symbolically. Phenomenal. Awesome. You know what we should do? Let's do it again. All right. X squared plus 8x. What more do we need? How many ones do we need in order to make this a perfect square? So we've got x squared. We've got 1, 2, 3, 4, 5, holy cow, 6, 7, 8. All right, let's start building a square. Now, one thing I'm thinking right away is, you know what? If we want to build a square, we're going to want to have 4 x's going this way and 4 x's going that way, right? It's got to be the exact same number of x's on the length as the width in order for it to be a square. So I immediately know that we're going to have 4 of these x's be kind of vertically oriented. So, you know, it's just half of them, right? We're going to have half of them be vertically oriented, and we're going to have half of them be horizontally oriented. So I'm just going to take 4 more horizontal ones and get rid of these ones. So we've got 1, 2, let's get them, 2, 3, 4. And in general, I think we're probably just going to have to go half and half every time if we want to make a perfect square. All right. So we've got the outline of a square. The question is, how many of these ones do we think we're going to need to complete it? Do you have a guess? You know what I think? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Interesting. We always do need to add kind of a square on its own. I'm going to just use this feature, right? We kind of have to, what's missing is itself a square. Interesting. And that was the case here too. We had a 3 by 3 square that we were missing. Here it happens to be a 4 by 4 square, definitely going to be 16 ones. Amazing. So what does that mean? It means that if you have x squared plus 8x and you want to complete that square, it means we need to add 16. And what is the perfect square we get? You guessed it, x plus 1, 2, 3, 4 squared. Now, after these first 2 examples, I hope you're beginning to see a pattern here of how we take something that isn't a perfect square and transform it into one. Let's do another one anyway. Maybe we can make some predictions. All right, x squared plus 12x. Yowza. I think preemptively I have to zoom out a little bit because, well, I think we need a bigger square. So, x squared plus 12x. Now I'm thinking, if I have 12 of these x's to go and I need to build a square, yep, I'm going to need 6 of them over here and I'm going to need 6 of them over here. All right, and you know what I'm thinking? I'm thinking that our eventual square that we're going to create, this one right here, you know what I think the dimensions of that square are going to be? X plus 6 times x plus 6. So we're going to kind of do this one a little bit out of order. I think we're going to end up with x plus 6 quantity squared. Very interesting considering how we had to kind of break this 12x in half to get, 6 of them here, 6 of them there. It's also what happened here. We took the 8x, we kind of split them up in the two directions. We had 4 here, 4 there, x plus 4 quantity squared. And similarly, we split up these 6x, 3 here, 3 there. All right, just trying to see if we can find any patterns. So we still need, though, some more ones in order to make a square. We need, well, these. And this itself is a square. And I wonder if you already know how many ones it's going to take. Well, let's see. 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6. We're going to need 36 of them. All right, so if we wanted to complete the square for x squared plus 12x, we would need to add how many ones? We would need to add 36 ones. Yowza! And we'd end up with a quantity of x plus 6 squared. So maybe you're starting to notice a pattern here. I hope you are. And let's continue with this and see if you can make some predictions. Now, I do want to make a note that visually we've dealt with all positive quantities. X squared plus 12x, x squared plus 8x, x squared plus 6x. We haven't really dealt with any negative quantities, but I want to show you that it's actually going to be the exact same sort of thing. So if I had x squared minus 6x, I'm going to kind of, it's a visual representation. It doesn't really make as much intuitive sense with regard to area, but it's the same sort of deal. What's interesting is, right, we still have a square going on here. Definitely going to be a square. What are the kind of dimensions of this square? Well, I think we have, an x. That's obviously this dimension. But it's interesting. We have x minus 3. Negative 1, negative 1, negative 1. Hopefully I can, nice, get that to work. So actually, this is going to end up being x. You could say x minus 3 quantity squared. You could also say x plus kind of negative 3 quantity squared. So either one is fine. I just want to show the kind of analogies to how they work. And note to self, in this particular situation, it still makes sense that what we need to add right here, well, that's still going to be a square. I'll make this one, I don't know, purple, just for fun. It's still going to be a square that we need to add. And note to self, negative 1 times negative 1, if we're kind of talking about area or dimensions, it's kind of weird, but that's still 1, right? This is still a positive 1. And so we end up with still adding, just like before, we're still going to add 9 in this case. So it's actually going to be the exact same sort of thing, and you can use the exact same intuition whether or not you are dealing with positive or negative quantities. So I'm just going to put in that 9 there. Remember in our very first example, I think we had to add 9, and it actually was the exact same number that we had to add with x squared minus 6x. And I mean, you can confirm for yourself, right? X minus 3 quantity squared is, when you multiply this, you get x squared minus 6x plus 9. So here is my question to you, is have we found a pattern? Maybe we found a pattern. I hope we have. And I've kind of been trying to lead you towards it with the way that I've been describing these situations. And I think that, for instance, if you ever have a polynomial of the form x squared plus something, plus something times x, whatever, I'm just going to say bx. I don't know what that is. What have we done every time? Well, remember that every time, for instance, I'm going to use this specific example, when we had 12 x's, we had to split them in half, right? Put 6 of them over here and 6 of them over here. And that's why we ended up with x plus 6 squared. Whatever this coefficient was, in this case 12, in this case 8 to 4, in this case 6 to 3, and even in this case, negative 6 to negative 3, we took half of them, and that was the thing that went here. So I'm going to call this b over 2. Right, we had to take half of this, like 6, and 6 squared was, we had x plus 6 quantity squared. What was the number in green that we had to add? Well, we had to add, I'll make this in green just for consistency's sake. We had to add that number, in this case 6 squared. Right? In this case, we had to add 4 squared. In this case, we had to add 3 squared. And so I hope that this generalization right down here is not kind of earth-shatteringly new that maybe you already knew that was coming already. But this is how we kind of complete the square, thinking about it like formal symbolic notation. But I always want you to consider these kind of representations as well. And I want to show you that this works even in, well, you could do this one. We're going to skip it. Even when we have like fractions going on. So note to self, if you had 3 x's to go around, you can't split that up super evenly. You would have to do 1.5 of them here, 1.5 here. So note that in this case, we are going to, all right, I'm going to do this after a little rotation. So I'm just kind of setting up our square just like we did with every other one, except now we're kind of delving into fractions, which is okay, right? So here is what I believe to be a representation of x squared plus 3x, right? We have a half, 1, 1.5, 2, 2.5, 3. What must we add? Well, we're still going to add a little square right here. What is that square going to be? Well, conveniently, I have a nice little 1/4 block here. We're going to have 1, 2, 3. I bet you can tell what's going to happen. We're going to have 9 of those little 1/4 blocks. We're going to have 9/4. I'm not going to call this 2 1/4. I'm going to call this 9/4. So interestingly, we had to add 9/4. It's kind of crazy. 9/4. 9/4. And what do we end up with? The perfect square is x plus 1.5, or x plus 3/2 quantity squared. And note to self, 3/2, when you square that, 3/2 times 3/2, 9/4. This also agrees with the generalization that we came up with right here. So I hope we're feeling pretty good about how to complete the square. Now let's do some practice problems looking at just the notation. All right, we're back with the guided notes. Here we go. So, like we said before, we now have a generalization for how to complete the square whenever we're given kind of what I sometimes dub 2/3 of a perfect square trinomial. Right? We're going to have to add half of that linear coefficient squared. And we end up with, I really don't like to use this notation very much. I think it's worth at least showing you this, but don't memorize this. If you're memorizing this, we have no idea what's actually going on. I want you to know what was happening before with all of our algebra tiles, for instance. And I want it to make sense. Of course, that's always the most important. Okay, so in this case, let's complete the squares. Some of these we've already done. In this case, I hope you know that we're going to have to add 9. I'm going to do a little bit bigger ink. And we're going to end up with x plus 3 quantity squared. In our second example, note how similar these two are, and we did both of these with the tiles. Very similar original polynomial, x squared plus 6x, x squared minus 6x. We're still going to have to add 9. That always happens. Think back to our algebra tiles examples. X minus 3 quantity squared. That's the only little difference, x minus 3 quantity squared as opposed to x plus 3. X squared minus 10x plus 25, right? We've got to take half of negative 10, which is -5, and that's the thing that's going to be squared. Right, thinking back to those algebra tiles always. X squared plus 2x, well, half of 2 is 1. 1 squared is 1. All right, feeling good. Let's see, x squared plus 4x, half of 4 is 2. 2 squared happens to coincidentally also be 4. All right, making moves, making moves. Half of -14 is -7. -7 quantity squared is 49. And you can always check by actually multiplying this out, expanding it, and I think you know that this is exactly what you're going to get. We're using a lot of intuition here. Half of -2 in this case is -1. -1 quantity squared is 1. Note to self, I think I mentioned this, we're always adding. If you're going to complete the square, you're adding some number. Half of -4 is -2. -2 quantity squared is 4. All right, 2 more. Geez, a whole lot of examples. Oh my God, we're almost done. So, all right, here we go. In all of these ones, we're actually going to now kind of dive into some fractions as well. So here we go. So here, I think we kind of have an x squared plus, 1x, if you will. Half of 1 is 1/2. So this is going to be x plus 1/2 quantity squared. 1/2 squared is 1/4. And let's go ahead and actually confirm this one. Because sometimes people are like, well, I don't actually believe this hocus pocus stuff. X plus 1/2 times x plus 1/2. Here we go. So x times x is x squared. X times 1/2 is 1/2 x. Another 1/2 x. 1/2 times 1/2 is 1/4. Holy cow, we actually do get x squared plus, well, 1x plus 1/4. Holy cow, it actually works. So it's just really important. I want you to feel comfortable taking this condensed version and knowing how it would multiply out, how it would expand, excuse me. All right, 3 more. I hope you're trying these on your own before I show you how to do them. In this example, half of -3 is -3/2, -1.5. That squared is 9/4. This is actually very similar to the one we did in our lesson video, with the tiles, that is. Excuse me. Whoa, here our linear coefficient is itself a fraction. What is half of 3/2? Well, I think half of 3/2 is a half times 3/2. Oh, that's, excuse me, 3/4. All right, so a half of 3/2 is 3/4. So 3/4, and 3/4 quantity squared is 9/16. Holy cow, we're going to confirm this one together by multiplying it out, and then we'll do our last one. So x plus 3/4, holy cow, multiplied by x plus another 3/4. All right, let's see. Holy cow, x times x is x squared. All right, not so bad. X times 3/4 is 3/4 x plus another 3/4 x. 3/4 times 3/4 is 9/16. So we've got the 9/16 down, all right. We've got the x squared, but what's going on with this 3/2? Well, let's see. 3/4 x plus 3/4 x is 6/4 x, which is indeed reduces to 3/2 x. So yes, wow, actually worked. No surprise there, though. Hope you thought it would work. All right, last one, here we go. Holy cow. Let's see, half of -5/3 is -5/6. That quantity squared is 25/36, and I will leave it to you to multiply and confirm that this is exactly how we would complete the square. So now I hope we are feeling very confident in our abilities to, well, complete the square. So I hope you found that helpful, and I hope you enjoy.